So in this lesson, we are going to learn how to prove the limits of functions using the precise definition of limits, or better still, the epsilon delta definition of limits. Now, to clearly understand how this proof is done, we are first of all going to consider functions of a single variable, and then we translate this same idea to functions of two variables. So first of all, let's look at the definition of limits for functions of a single variable. So, given that f of x is a function of only one variable, then the limits of that function, f of x, as x approaches a, is equal to L if for all epsilon greater than 0, there is a corresponding delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then we say that the absolute value of f of x minus L is less than epsilon. So this is the definition, that is the limits of f of x as x approaches a is equal to L if for all epsilon greater than 0, we are going to find a corresponding delta which is also greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is also less than epsilon. Now, using the definition of limits, the precise definition of limits, let's try to prove whether or not the limits as x approaches 2 of this function is equal to -1. So using the definition of limits, we say that the limit of this function as x approaches 2 is equal to -1 if for all epsilon greater than 0, there is a corresponding delta also greater than 0, such that if 0 is less than the absolute value of x minus, here we have a to be 2, is less than delta, then the absolute value of f of x, which is -2x plus 3, so -2x plus 3 minus L, which is -1, is less than epsilon. So actually what we are going to do here is first we need to find delta greater than 0, and then next we prove that the absolute value of f of x minus L is less than epsilon. So these are the two main things we are going to do here. So let's start the solution process. So we are going to let epsilon be greater than 0. So we let epsilon greater than 0, and then we consider this part of the inequality. Okay, so given that the absolute value of x minus 2 is less than delta, let's call this equation 1. Now we are going to establish a relationship between delta and then epsilon. But before we do that, we need to work out this so that we can later establish the relationship. So we are going to consider this part of the inequality. So we say that for the absolute value of f of x minus L, which is equal to that -2x plus 3, mind you, that is f of x, and then minus -1. Now let's try to simplify this. So this becomes, we have absolute value of -2x plus 3, negative, it becomes positive, so plus 1, and then this becomes absolute value of -2x plus 4. Now, looking from equation 1, we want to get something like the absolute value of x minus 2 here. So to do so, we are basically going to factor out -2, and then inside of the bracket we have x minus 2. Now notice that -2 times x is -2x, -2 times -2, that is positive 4. Here we have the absolute value of -2. Now the absolute value of a negative number is positive, so we are going to evaluate this and then pull out that. So that becomes 2 times absolute value of x minus 2 Now again, looking at equation 1, here we have the absolute value of x minus 2 is less than delta. Now if we should multiply the absolute value of x minus 2 by 2, that is what we have here. So if we should multiply this by 2, then it should also be less than multiplying delta by 2. Assuming that you have 1 is less than, let's say, 2. If you multiply 1 by 2 and then multiply 2 also by 2, then you realize that this is still, the left hand side is still less than the right hand side. So that is actually what we mean here. So if you should multiply 2 by the absolute value of x minus 2, then it should still be less than 2 times delta. So we are saying that this thing, okay, this thing will be less than multiplying delta by 2. So in actual sense, we have the absolute value of f of x minus L to be less than 2 delta. So let me write that here. Absolute value of f of x minus L is less than 2 delta. Now we'll come back to this inequality. This is very important to us. Now, looking at this, you realize that we have the absolute value of f of x minus L less than epsilon. Here we have absolute value of f of x minus L less than 2 delta. So in that case, if this, the left hand side is equal to the left hand side, then the right hand side is also equal to the right hand side. So we can say that epsilon is equal to 2 times of delta. Now in that case, since we want to find delta, we divide through by 2 and then we have delta equals epsilon over 2. So this is delta greater than 0. For any value of epsilon, we've been able to find delta greater than 0 because epsilon is greater than 0, it's a positive value, and so a positive value divided by 2 is still going to be positive. So we've been able to finish one part of the solution process, that is to find delta greater than 0. Now the next thing is to prove that the absolute value of f of x minus L is actually less than epsilon. So that's what we are going to do next. So from this inequality, we have absolute value of f of x minus L, and that is less than 2 delta. Now this time we have delta to be epsilon over 2. So we are going to fix that here. So we have absolute value of f of x minus L is less than 2 times epsilon over 2. So we cancel out these two, and then we have the absolute value of f of x minus L is less than epsilon. Hence the proof. So this is the end of the proof. At the end of the day, we've been able to prove that if the limits of this function as x approaches 2 is equal to -1, then for all epsilon greater than 0, there is a corresponding delta greater than 0, which we have here, such that if 0 is less than the absolute value of x minus 2 is less than delta, then we have the absolute value of f of x minus L to be less than epsilon. So that is actually what we have here. So we've been able to prove that indeed the limit of this function as x approaches 2 is equal to -1. So this proof relates to functions of single variables. Now we are going to translate this same idea to functions of 2 variables. So let's take the second question. So in this second example, we are going to consider a function of 2 variables, and we are going to prove using the precise definition of limits that the limit of this function as x, y approaches 1, 3 is equal to 11. So first of all, let's look at the definition of limits for functions of 2 variables. So we say that the limit of a function f of xy as x, y approaches AB is equal to L if for all epsilon greater than 0, there is a corresponding delta greater than 0, such that if 0 is less than the distance between xy and then AB, which is expressed as the square root of x minus a all square plus y minus b all square is less than delta, then the absolute value of f of xy minus L is also less than epsilon. So this is the definition of limits for functions of two variables. Now let's use this definition to prove our claim. So given that the limits of this function as x comma y approaches 1 comma 3 is equal to 11, we say that if for all epsilon greater than 0 there is a corresponding delta greater than 0, such that if 0 is less than, we have the square root of x minus, now a is 1 and then b is 3, so x minus 1 all square plus y minus 3 all square is less than delta, then we have f of xy, which is 2x plus 3y minus 11 is less than epsilon. So what we are going to do here is like we did in the previous example. We are going to find delta greater than 0 for all epsilon greater than 0, and then we move on to prove that the absolute value of f of xy minus L is indeed less than epsilon. So that's what we are going to do. So let's epsilon greater than 0, we are going to consider this part of the inequality, and then we say that given that the square root of x minus 1 all square plus y minus 3 all square is less than delta, and let's call this equation 1. Next, for the absolute value of f of xy minus L, now this is equal to that. So here we are supposed to have, the bars here on both sides, so that's equal to 2x, the absolute value of 2x plus 3y minus 11. And let's try to work on this. So looking at equation 1, you realize that here we have x minus 1, and then this side we have only x. So we need to manipulate this x such that we get something like x minus 1. So we have the absolute value of 2. Now we are going to express x here as x minus 1 plus 1. X minus 1 plus 1. Now x minus 1 plus 1 is still x, so it's actually the same thing. And then we have plus 3y minus 11. Next, we are going to multiply 2 by this one. Since we want to maintain x minus 1, we are not going to touch this x minus 1. However, we are going to multiply 2 by 1 so that we have the absolute value of 2 into bracket x minus 1. So we want to make this thing remain, and then plus 2 times 1, which is 2, plus 3y minus 11. Next, we have the absolute value of 2 into bracket x minus 1 plus 3y, and then 2 minus 11 is negative 9. Now automatically you realize that we can as well manipulate this thing so that we have a scalar times y minus 3. So this becomes the absolute value of 2 into bracket x minus 1 plus, we can factor out 3 so that inside of the bracket we have y minus 3, just like this. Now at this point we can use one of the properties of absolute value to modify what we have here. Now here we have the absolute value of 2 into bracket x minus 1 plus 3 into bracket y minus 3. So we can make this to be equal to the absolute value of a plus b. Okay, so this is a and that is b, and we say that this is less than or equal to the absolute value of a plus the absolute value of b. Okay, this is less than or equal to the absolute value of A plus the absolute value of B. So actually, we are going to have this, okay, this whole thing, that is what has been expressed as this here. So this whole thing should also be less than or equal to the absolute value of 2 into brackets x minus 1 plus the absolute value of 3 into brackets y minus 3. Okay, and notice that on the left hand side we have the absolute value of f of xy minus L, and again we can pull out the constants so that we have the absolute value of f of xy minus L is less than or equal to, we pull out this, we have 2 times the absolute value of x minus 1 plus 3 times the absolute value of y minus 3. So from equation 1 we have x minus 1, we also have x minus 1 here, and then we have y minus 3, we also have y minus 3 here. So let's do that on the next page. So from equation 1, here we have the absolute value of x minus 1. So the absolute value of x minus 1, we say this is equal to the square root of x minus 1 all square. Now this is another property of the absolute value. So whatever value that we have here, the absolute value of this value you have here is equal to having the square root of the square of that particular value. So this is a property of the absolute value. Now if this is the case, then we say that this thing on the right hand side is always less than the square root of x minus 1 square plus any other thing which is non-zero. Now looking at equation 1, we have y minus 3 all square, so we are basically going to put that here because we need to draw a relation at the end. So y minus 3 all square. Now what this means is that so long as you have the square root of x minus 1 all square, that is less than the square root of x minus 1 all square plus something which is non-zero. Okay, plus something which is non-zero. So the left hand side is always going to be less than what we have on the right hand side here. Now also from equation 1, we say that the square root of this, okay, is less than delta. So that is what we have here. The square root of this, we say it is less than delta. So actually we have the absolute value of x minus 1, to be less than delta. We call this equation 2. Now again from equation 1, we have y minus 3, and then here we have y minus 3. So we say that the absolute value of y minus 3, which is equal to the square root of y minus 3 all square, this time we are saying that it's also less than when you have the square root of x minus 1 plus y minus 3. Okay, this is also less than that. And then from equation 1, you realize that this is less than delta, so we still have this less than delta. In actual sense, we have the absolute value of y minus 3 to be less than delta. Let's call this equation 3. Now the next thing we are going to do here is we are going to call on this inequality. This is very important to us. Okay, so let's quickly rewrite this on the next page. So we have now let's look critically into this inequality and then try to make inputs from equation 1 and 2. Here we have absolute value of x minus 1. Here we have absolute value of x minus 1. Now we are saying that the absolute value of x minus 1 is less than delta. Now here we have 2 times the absolute value of x minus 1. So if you should multiply this by 2, then we say that it is still less than 2 delta. Okay, it is still less than 2 delta. Therefore, 2 times the absolute value of x minus 1 is less than 2 delta. Okay, and then plus, from equation 3, we have absolute value of y minus 3 is less than 3. Here we have absolute value of 3 times y minus 3. So if you multiply this by 3, then this is less than multiplying this by 3. Therefore, we say that what we have here is going to be less than, okay, it's also going to be less than 3 delta. Okay, and don't forget, we have on the left hand side f of x comma y minus L. That is the absolute value of this. Great. Now let's try to add these two. So we have the absolute value of f of xy minus L, and that is less than 5 delta. Now we have absolute value of f of xy minus L less than 5 delta, and then here we have absolute value of f of xy minus L less than epsilon. Therefore, we can establish a relationship between epsilon and then delta, because the left hand side is the same. The left hand side is the same, and so the right hand side we can say is also the same. Therefore, we say that epsilon is equal to 5 times delta. Now in that case, since we want to find delta, we divide through by 5, and then we have delta to be equal to epsilon divided by 5. So this is the value of delta for any epsilon greater than 0. So this is one part of the solution process. The next thing is to prove that indeed the absolute value of f of xy minus L is less than epsilon. So that we are going to do here. So we have the absolute value of f of x comma y minus L is less than. So from this inequality, we have 5 times delta on the right hand side. Delta is epsilon over 5. So we cancel out 5 and 5, and then we have the absolute value of f of xy minus L less than epsilon. Hence the proof.